So good afternoon, everyone. My name is Luciano Meirelles Santana. I actually am a PhD student from Paris. Today I'm pleased to present you my work in testing gaseous hydrogen enrichment is using suicide refraction toughness test. So we already talked a little bit about this today, but the conversion of natural gas pipelines to transport hydrogen with blending or not is a crucial question to the success of the transition energy toward the renewable source. The one problem that we have about this is that we have to characterize the hydrogen embrittlement susceptibility of these steel pipelines. But there is a huge problem because only in France we have 40,000 kilometers of natural gas pipelines. So to do this characterization, it would be very costly. So the Messier project proposed a different approach. It proposed to take a small couple of the material directly from the structure of the pipeline without the need to interrupt the production. And from these small couples, machine mini specimens that will permit to characterize the mechanical properties of the pipeline. But when we talk about mini specimens or some size specimens, usually I say mini specimens, we have some issues that are related to the size of the specimens. Some of these issues, first is the machining. As the specimen is very small, maybe it could have some effect of machining in the specimen because the induction of the residual stress, for example. We could have also dispersion of the results because they are very small. They could take separate parts of the material. And also about the validity of the toughness test, because we know that the validity of toughness tests are also related with the thickness of the specimen. And as it was not enough yet, we have the hydrogen also, because we tend to do this test with gaseous hydrogen. So we have developed innovative test setup to perform the test of mini specimens in gaseous hydrogen. So today I will present some results of the soil tests with many specimens, different size of specimens, and different hydrogen pressures, and also toughness tests with mini specimens with different steel pipelines materials and different hydrogen pressure. So the materials, we have two steel pipelines, one vintage and one modern. The microstructure is pretty much the same, it's very thick. Both are equivalent to 52 steel, grade steel. But the main difference is in the, this is what? Yes, is the content of sulfur that reflects in the average volume fraction of inclusions. So we have a way more inclusions in the vintage steel than in the modern steel. And we expect that it will change the mechanical properties. So geometries of the specimens. So I will present results with a standard tensile specimen. Sorry. With standard tensile specimen that has 4 millimeters diameter and 20 millimeters of gauge length. Actually, I brought some specimens to show to you. So I will pass. There are 4 specimens here that are a mini tensile specimen. You can pass. This is a standard toughness specimen. This is to compare the mini toughness specimen that I present there. And to compare here the standard tensile specimen. So present two geometries of mini tensile specimens with 2.4 millimeters and 4 millimeters of gauge length, And mini specimens with 1.2 millimeters of diameters and 2 millimeters of gauge length. And also the mini toughness specimens that has width of 10 and the thickness of 5 millimeters. So first of all, to do the validation of the mini size specimens, we perform some tests in there in the MTS machine with extensometer control the environment in air condition. And we swim and we follow the local stray, I mean the netting, with the edge trace technique where we put a camera and a heterolight to follow the contour of the specimen, and so we can have the information of the radial strain. So the results shows that the global plasticity is affected by the geometry of the specimen. We can see here that the two mini specimens are here, and the standard one are here. So we can assume here that the ductility is increased for the mini specimens. But when we see the global plasticity, we can see that it is independent of the specimen geometries. Here we have the stress plotted against the radial strain, that is this thing here. We can see that they are equivalent, and doesn't matter if it is a standard specimen or mini specimen, and it is not affected by the machining process also. That is a concern. Now talk about hydrogen embrittlement. So here I have to spend a little bit of time. So this is our test setup for mini specimens and gaseous hydrogen. So the heart of this test setup is the pressure chamber, but because they have is a pressure chamber with 4 sapphire windows, and we can play with these windows to put cameras and lights to do the edge tracing technique during the test pressurized with hydrogen. And we can follow what we want here. Here I show the one example with a mini toughness test where I can follow the line load opening displacement and also the angle displacement. And this is associated with a controller, the KS controller. And this controller has a communication with the MTS machine. So we can adjust the displacement rate of the MTS machine with the information of the optical system. That is the innovation. And also the MTS machine was designed for slow strain rate tests. We can play with hydrogen, helium, and nitrogen up to 250 bar. Then we have also the possibility to do gas analysis, oxygen and moisture. We usually do before and after the test to control the quality of the gas. Since we know, we already talked about it today, that the impurities of the gas can affect the effect of hydrogen embrittlement. And also, as we have the information of the LOD and the opening angle, we can directly calculate the CTOD of the test using the methodology that is equivalent to the double clip by ExxonMobil. But instead of using 2 clip gates, we can use the angle, and by geometrical structure we can achieve the CTOD. Good. Some results for the SIO test, mini SIO test with the modern steel pipeline in there, 100 bar of hydrogen and 200 bar. So we can see here the effect of pressure, so higher pressure, more embrittlement. We can see also the effect of the specimen geometry. So I here showed the results for 2.4 millimeter in the square, and in the round one is the 1.2 millimeters. We can see that smaller the specimen, more pronounced is the effect of hydrogen embrittlement. And also we can see here that as we already told today, The hydrogen embrittlement index that is calculated with the restriction of the neck or the reduction area is more sensitive to hydrogen embrittlement. So here I show the fracture surface. In there, we have the typical ductile I would expect. And we can see that from 100 bar, 200 bar, we can see several extracts, 100 bar and 200 bar. For 100 bar, we can see the surface, the 100% of quasi cleavage, and there is a smooth transition onto the center where we can see the microvoid coalescence feature. But those dimples that we observe here are smaller than the dimples we observe in air condition. And when we compare with 200 bar, we can see that we have in almost all the fracture the quasi cleavage feature. But if we pay attention here, we can see very, very small dimples that are even smaller than the dimples with the 100 bar. Now some toughness results for the modern material. So the white one is in air. We can see that the J02 millimeters is above the limit of validity, so it's not a valid result if you analyze according to the standard. But when we expose this material to 100 bar of hydrogen, the G02 is already the valid zone. That is something interesting. And when we increase this pressure to 200 bar, it is still more irritant. We can see also the results for CTOD. That is interesting because at 200 bar, we have, we can say a popping here in the, just the beginning of the plot. And we consider this as the critical CTOD in this situation that leads us to a very high hydrogen embrittlement in 200 bar. Again, we see the fracture of these specimens. We can see in there the typical ductile behavior. We can distinguish between the pre-crack, the blunting, and the propagation. The beginning of propagation, we have only microvoid coalescence. When you see 100 bar, we can still see the pre-crack, the blunting, and the propagation. But in the beginning of the propagation, we have a mixed aspect where we can see the coexistence of microvoid coalescence and quasi cleavage that affects radiant toughness. When we see at 200 bar, there is no blunting zone here. We can see that the crack goes directly from the pre-crack to the propagation, and the beginning of propagation is 100% quasi cleavage. That is coherent with the popping we see in the plots. Now for the vintage material, the result in air is already in the zone of validity. Actually, I didn't plot the zone of validity here because the plot would be very funny, but the limit is 280, and I found here with around 50. And when we put hydrogen pressure, doesn't matter if 100 bar or 200 bar, we arrived at a saturation of hydrogen embrittlement. Okay. When we see here that the CTOD values are very, very low, it's less than 0.05 millimeters. So it's a material that is very, very little. And we can see this in the fracture surface. We can see here that we need higher magnification to see the blunting in there. And we cannot see the blunting in 100 bar, 200 bar. And at the beginning of the propagation, we see all the quasi cleavage fracture. And we can see also these veins that are related with the inclusions of this material. So, passive talk, I presented here an innovative test setup to test mini specimens with a hydrogen, gaseous hydrogen environment. we found by performing the integration of optical exometry with the test machine control, no significant size or machine effects were observed in the tensile tests. We corroborate the works of our colleagues that the embrittlement index that is linked to the restriction is more sensitive to hydrogen embrittlement. And we can see also that the result with hydrogen for many toughness specimens are already the validity range. The careful interpretation of the result is crucial because it's a new methodology. So that's it.
Thank you very much. So